but below the surface, meaning the graph. So that's why we're going to use the double integral. So moving on, I set up the double integral v equals. So I put the double integrals x and y. I left the z out, so because z equals x and y. So we're going to do, of course, it's dx, dy, because it's x in respect of y, because it's double integral. So I use the points given, the coordinates, that's what I call them, as a and b again. And we know the integral format, it's b over a. So
The intervals.
yeah,
Hold on 1 second. The interval. So the rectangle region is 0, 1, cross 0, 1.
yes,
Those two are intervals, not points. Especially
yes.
use bracket. Yeah.
So this is how I set them up. So as we move on, I separated them into two parts while solving them. So I put the y with the dy and the x with the dx, which makes more sense. And I solved them separately. So I first integrated the y dy and then x dx. When you integrate the y, you get y squared over 2. Same for the x squared over 2. Then you have to plug in the 1 and 0, and you have to subtract them to get the output. So when we plug in the 1 for the y squared over 2 minus 0 squared over 2 is the same thing for the x. For both of them, they compute the outputs come out to be half and half for both. And
Hold
since
on. Hold
yeah,
on. What's half square?
half squared right here.
Yeah. Yeah.
So what I did here is, so
Half
you
square
see
is
how,
half. No, your calculation. Half
yeah, yeah.
square is not half. Half square means half times half.
So you're
You have
talking about the
half
calculation
square.
itself.
You have half square here, right? What's half square?
Okay, so I know what I did. So it's not
Oh,
the,
okay, okay.
it's
So
the
it's
one
one
squared.
square.
I didn't put
One
the,
square over two.
yes. So it's just the
Oh, yeah,
y
you're right.
squared. It's not the
Yeah,
y
you are
over.
right. It's one square.
Yes, I
Yes,
didn't
you are
put
right.
the, yeah. So I didn't put the parentheses. So it's half and half, and of course they're being
Yeah,
multiplied. So when we multiply half and half, you get 1 over 4th. So 0.25. That is the region over the rectangle and under the graph. That's the final volume, and it's confirmed by the
nice,
book right here.
nice. Okay, good. Thank you.
You're welcome.
Okay, Gregory, are you ready?
Yeah. Can you hear me?
Yes.
Okay, great, lovely. I will share screen now. Okay, great. Can we all see this? Yes, okay,
Yes.
great. So I'll be presenting section 5.1, number 5. And so here's our question. Using Cavalari's principle to show that the volumes of these cylinders with the same base, so the cross section here at the bottom and the height are equal, we want to show that the volume is the same. So one thing that we should notice or preface is that we can place these cylinders at the same level, right? And then we're also going to need the cross section of the area of any slice in the horizontal direction. So that'll result in a circle, right? We can see it right over here. And we also need the volume of a cylinder because we want to prove that the volumes of these cylinders are the same thing. And so we can look at this picture and see that each cross section will result in a circle. And if we sum all of those circles with the height of dy, right? This goes back to like calculus 2. If we sum over all these areas, then we can get the volume of one of these figures. And thus calculating the volume of a cylinder, we have to sum over all these heights of circles with all the areas. And since we have two of these circles on like each plane, if we put these at the same height, the circles will always represent the same height with the same volume, given that the radius is the same because the base is the same. Then we can just say the same thing again. We place them at the same height for cylinder A and cylinder B, where cylinder B is one that's a little bit slanted, but we have to verify if the area is the same. And we know that the volume, sorry, not the area, but the volume. If all the areas are the same, then if we sum up everything, the volumes will be the same. And so for figure 1, we know that one cross-section area is pi r squared, which is the area of a circle. And if we integrate that with respect to height, which I said before would be dy, but in this case, the height will be y or h, whichever variable you want to use. You integrate with respect to that. And we can apply linearity here with pi r squared. And any constant multiplier gets ignored by an integral, so we can just move straight past that. And we have a 1 dh, and we can integrate our function here, which is 1, and we get h as the evaluation here, and this will be for figure A of this one, and it would be the same thing for cylinder B. We would have to do a cross-section area and sum up all the heights, and we know that since the bases are the same, the radius is the same, and we have the same height, then we know definitely for sure that the volume of figure A here should be the same volume as figure B. And that's all. Thank you.
Nice. Okay. Thank you.
No
That's
problem.
Gregory.
Yeah.
Oh, Ryan. Ryan next, section 217. Then Mahama Babu 5, section 115. Then Adam, section 1, Yuri. Oh, Adam, I'm not quite sure 511 is already presented. I had the impression it's already done. Let me see. Yes, Dieli did yesterday, 5.11. Adam, you need to pick another one.
Okay.
5.19.
Do I still keep like my spot and where I'm presenting? Because I could just choose a different
Yeah,
one.
yes,
Okay.
yes, just choose another number.
Can I begin?
Yes, Ryan.
Okay, so my question asks us to, it basically gives us this integral, and it has 0 and 1 acting as A, B, and C, D, and it basically swaps them around, as you could tell by the dy dx and dx dy, because according to Fubini's theorem, it can. And it basically asks us to prove through a substitution involving tan how this becomes pi over 4 and this is negative pi over 4, and then why it doesn't, and then prove why it doesn't actually hold here, why Fubini's theorem is, I guess, not contradicted, but just doesn't apply in this scenario. So the first thing I did was I did a tan substitution, just like we did in Calc 2. Since I'm integrating with respect to y, my x is a constant, so my y becomes x tan theta, and the derivative of that is x secant squared theta. And then I basically get this monstrosity, which through basically wiping out these x's become x to the 4th, so we can pull out 3 x's from there, and then 3 x's from the numerator, and so we basically get 1 minus tan squared theta over x secant squared theta. by replacing tan squared theta with sine squared theta over cosine squared theta, and by replacing secant squared theta with 1 over 1 over cosine squared theta, we can basically get cosine squared theta minus sine squared theta, which is equal to cosine 2 theta. I also pulled out the 1 over x that we had from here because x is just a constant for now. And cosine 2 theta basically becomes 1 over 2 sine 2 theta. I plug theta back in from here. So I basically got theta equals arctan of y over x. Then by some funky identities, this whole thing basically becomes y over x squared plus y squared. And plugging in 1 for y and then 0 for y and then basically solving, it basically becomes it becomes arctan. Oh, I'm sorry. I simplified first, which is 1 over x squared plus 1. Then I plugged in. And so it's arctan of 1, which is pi over 4, minus arctan of 0, which is just 0. Then doing the same thing, but with respect to x, it basically ends up being the same thing, except we have this negative here. So because of that, going through all the substitutions, the numerator is reversed. And because of that, we pick up a negative over here on the constant. And because of that, when we eventually get back to 1 over x squared plus 1, it's actually negative. So in reality, it's negative pi over 4. So how come these don't add up even though Fubini's theorem says that they should? Well, it's because the original function actually is not continuous, which is stated right here. Let f be a continuous function. On top of that, for theorem 3 prime, it says that the discontinuities could be sort of placed into a graph, like almost like just a point discontinuity where the rest of the graph exists and like the number should be 2.9, then 3, then 3.1, and really just 2.9 to 3.1. But in this case, that doesn't happen because the discontinuity is actually infinity, and it's not bounded either. In fact, when you graph it, it looks like that. So approaching on the y-axis, you actually go to positive infinity, or I'm sorry, I believe that's the x-axis. Approaching on the x-axis, you go to positive infinity, and approaching from the y-axis, you go to negative infinity. In fact, if you try to do L'Hopital's rule on this, and let's say you go along the path x comma 0, then you get x squared over x to the 4th, which eventually becomes 1 over x squared, which just goes to infinity. You can't take L'Hopital's rule unless it's 0 over 0. And in that case, it's 1 over 0. And so you're out of luck. And as you can see, it goes to infinity. So that's why Fubini's theorem actually doesn't apply here. So it's not broken per se. It just never existed for this problem in the first place.
Very nice. Very nice. As you can see, Ryan is pretty advanced. Thank you, Ryan. Okay.
Thank you.
Muhammad Babu, 5.115.
All right, can you hear me?
Yes.
Awesome. Give me one moment. Let me just share my screen.
Okay.
Share content. Share screen. All right. Can you see my screen?
It's getting up. Yes, now.
All right. So give me one moment. All right. So you see the.
Yes, very
All right.
clear.
So I'll give it one moment. So I'm doing question 15, and for this question, we're supposed to repeat exercise 14 by repeating. So the question that's going to come afterwards from me, we're going to repeat that. But we're trying to find, I guess, the area of a cube. We're trying to find the volume, if I said it correctly. And we're going to use this formula to find it. Well, so from the rectangle, so that's going to be from, so for the x-axis is going to be from -1 to 1. That's the interval for the x-axis, and then the y-axis is going to be -3 to -2. Here I have the integral right here, and we just do it by pieces. So the first piece will be the x-axis. So I did it from here, did -1, integrated from -1 to 1, and I got this. And then after I finished, I did the math for this one and got it to here. So this is, I then add it to here. So then we could get it for the y-axis as well. And then after I do the calculation, it was very hard to calculate because we had a lot of fractions here. I got to, so the area I got was 160 over 15, and I simplified it to 32 over 5.
Okay. Yes. All right. We don't call this formula. It's function. F of xy equals x to the fourth plus y squared. We don't call it formula. We call function.
Function, yes.
Yeah. Okay.
Thank you for
Yes.
that.
Very nice. Right. You're integrating with x direction first and then y. Yes. Nice. Okay. Adam, are you ready?
Yeah.
Which number you pick?
Question 4, 5.1.4.
Okay. Yeah, go ahead.
Okay. So I want you to evaluate this integral from 0 to pi over 2, 0 to 1, and then y cos x plus 2. So I started off doing the with respect to y, and it would become, well, this, and then, wait, is there a way to draw? Oh, there we go. It would become this, and then I took it out and did cos x over 2, and then just left the y squared on its own. Same here. I kind of isolated the y's, and then I evaluated from 0 to 1, and then after that, it came out to cos x over 2 plus 2, and then I evaluated with respect to x, where it became sine x over 2 plus 2x, and then I evaluated from 0 to pi over 2 to get a final answer of 1/2 plus pi. Wait, I think. I think that should actually be negative. Sorry.
Which one? Yeah.
The sine x, because unless.
No,
Oh, never mind. No, I got it backwards.
It's
Sorry, that's the derivative, not the integral.
right. It's positive.
No, I'm sorry.
Sine, that's 1, that's a
that's
half.
right.
0, that's pi. Yes, nice. Thank you.
Thank you.
Yuri, 5.38, then Walter, Israel, Tanya, Ivy, Liz, Gabriel, and Jun E.
All right, so I'd like to present question 8 from section 3, chapter 5. And the problem is the following. Let D be the region bounded by the positive x and y axis, and the line 3x plus 4y is equal to 10. And the problem asks to solve the integral over here. The integral itself is not complicated to solve, but the only complication here is the boundaries of the integrals of the double integral. So we need to figure out the limits of integration with respect to x and with respect to y. So to do so, I draw the graph of these lines. So it's positive x axis and positive y axis, which is over here, and the line 3x plus 4y is equal to 10. So I just rewrite this function in this form so I can use it later, and this line is here. So this blue triangle is my region, a region under which identifies the boundaries for the integral. And what also is unknown is this point, which is indicated here as 10⁻, but it's originally unknown. So I found it first. It's just the point of intersection of the graph of the line with x-axis. At this point, y is equal to 0. So I just use the original equation, substitute 0 for y, and then I find x. So I find that this point is 10⁻, 0. And I will be using it for the boundaries later. So from this graph, we can see that the x variable, the boundaries for x is from 0 to 10⁻, and for y, the upper limit is the graph, which is 10 plus 3x over 4, and the bottom limit is just the line y is equal to 0. So now we have we can rewrite this original integral as the following. I chose to use notation dy dx. That means that I will be integrating with respect to dy first and then with respect to dx, because we do inner integral first. And that's why over here I have the limits for y, and over here I have the limits for x. So for x we have the from 0 to 10⁻, and for y we have from y is equal to 0 to y is equal to 10 minus 3x over 4. So what I do next, I integrate the function x squared plus y squared with respect to y to get this function, and then I evaluate this function, this integral, using the boundaries from 0 to 10 minus 3x over 4, and at the end the result is here. And then I have to take the integral of this resultant function with the limits of the integration from 0 to 10⁻, because I integrate with respect to x, and that's why I'm using the boundaries for x, not for y. Again, the result is presented here. Then I just used calculator to calculate the number, and the approximate answer is 12.1. That's it.
All right. Thank you. Yes, very clear. Thank you, Yuri. Walter next, then Israel. Tanya.
Okay, so I'm doing problem 11 from section 5.1, where we're asked to elaborate a double integral of a function. And we're also given that R is a rectangle with dimensions along the x and y axis to 0 and 2 and -1 and 0. And so we can start the problem by first substituting these endpoints into our integral. And then we would start the problem by first finding the inner integral in terms of y, and then the outer integral in terms of x. And so we'll get an expression, the integral from 0 to 2, brackets the integral of -1 to 0 of -x e to the x sine, parentheses, pi y over 2, close parentheses, dy, close brackets, dx. And so we will start, like I said before, we will start by solving the inner integral in terms of y. And so in doing so, -x e to the x would be considered a constant. And so we can just take out the constant outside of the integral, and we will be left with the integral from -1 to 0 of sine pi y over 2 dy. And that would just equal to negative 2 over pi cosine pi y over 2 elaborated from negative 1 to 0. Here, I just took out the constant here from which is negative 2 over pi. And so we would just elaborate cosine pi y over 2 from negative 1 to 0, which I got is basically cosine of 0 minus cosine of negative pi over 2, which is just 1 minus 0. So 1 times the negative 2 over pi is negative 2 over pi. Then multiply that by the constant we took previously, and we will get x e to the x pi, 2 over pi. Then we will start solving the outer integral in terms of y. So it will be that form, that function, but the integral will be from 0 to 2. And so we get the integral from 0 to 2 of x e to the x 2 over pi dx. And we will take out the constant like we did before, which would be 2 over pi. We will have the integral from 0 to 2 of x e to the x dx. Here we will actually use integration by parts, since we have both functions in terms of x and we can't really find the integral of that. So I set my u into x and my dv into e to the x. My du becomes 1 dx and my v becomes e to the x. And so the formula for integration by parts would be uv minus the integral of 0 to 2 of v du. And so I would get 2 over pi as my constant, parentheses, x e to the x elaborated from 0 to 2 minus the integral from 0 to 2 of e to the x dx. And I got negative 2, not negative 2, 2 over pi, parentheses, 2 e squared minus parentheses, e squared minus 1 close parentheses. And then I just simplified it and reorganized it, and I got a final answer of 2 over pi, parentheses, e squared plus 1, close parentheses.
Wonderful, nice. Thank you, Walter. Okay, Israel next, Tanya, Ivy, Liz, Gabriel, Yi.
Okay. Sure. Okay, so all I really have to present is just a simple question. Just ask us to evaluate the double integral. And the initial integral that I asked us to solve is 3x plus 2y to the 7th power from 0 to 1 for dx and from 0 to 1 for dy. So I just start off with obviously evaluating the inner integral for dx, giving me just 3x plus 2y to the 8th power over 24, and I just take out 1/24 just to make my life easier while evaluating it, and I then plug in the values that were given, and that results in having 2y plus 3 to the 8th power minus 2y to the 8th. I don't really show that I evaluated it as two different integrals that are one subtracted from the other, but that's essentially what I did from the middle step to the second step after. And from then I just plug in all the values once more, and it's really just the algebraically heavy question. It just asks you to just, I took out 1/18 again just to simplify everything, and it's just really big, a really huge number that just comes out to like basically 1,932,930 over 432, which just simplifies out to 35,792 over 8. And that's really all this is.
All right. Thank you, Israel. Tanya.
I'm presenting from section 5.1, question 14. It says to find the volume bounded by the graph of fxy equals 1 plus 2x plus 3y, the rectangle 1, 2 to 0, 1, and the 4 vertical sides of the rectangle are. So first, I realized so it said to find the volume, so that would have to be a double integral. So the double integral of the function dA. So In this case, I did the integral 1 to 2, and then the second integral 0 to 1, and then the function 1 plus 2x plus 3y. And I first did in respect to y, and then in respect to x. And then after doing the integrating, then I got, after evaluating, I got y plus 2xy plus 3y squared over 2. Then I evaluated the integral from 0 to 1, and I got 1 plus 2x plus 3 over 2, and that was in respect to y. So now I'm going to do it in respect to x. So the integral is going to be 1 to 2, and then the function is 2x plus 5 over 2 dx. And then I evaluate that, and I do 2, and I got 4 plus 5 minus 1 plus 5 over 2, and then it's 9 minus 7 over 2, and then the answer is 11 over 2, and that's the volume.
Thank you. Thank you, Tia. Ivy. Then Liz.
Alright, so I'm doing 5.1.9, and for this question it's asking for a double integral of x squared y squared plus x dy dx. And from what we learned yesterday, if it's dy dx, the format for the double integral is going to be a, b, and a c, d for the inner integral. So we're going to integrate the inner integral from -1 to 0 from x squared y squared plus y. And from that, we get x squared y cubed over 3 plus xy. And we're going to find that integral, and we get 0 plus 0 minus negative x squared over 3 minus x dx. So since we integrated from respect to y, we're going to integrate from respect to x now. And from that, we get the integral from 0 to 2 from x squared over 3 plus x dx. And that integrated will give us x cubed over 9 plus x squared over 2. When we find the integral of that, we get 8 over 9 plus 2 minus 0. When we calculate this, we get 26 over 9.
Nice. Okay, that's Ivy. Liz. Then Gabrielle. And Jun Yi.
I changed my question. I'm gonna present something similar to what has been presented right before me. So this is 5.2, number 11. We want to compute the volume of the solid bounded by the graph z equals to x squared plus y, the rectangle or equals to 0, 1 times 1, 2, and the vertical side of or. So the volume gonna be equals to the double integral of x squared plus y with respect dy dx, going from 0 to 1, then from 1 to 2. So we're gonna start by integrate with respect to y. We're gonna start by the inner one. So when we integrate x squared plus y, that's give us x squared y plus y squared over 2. We evaluate this from going from 1 to 2. That's give us 2x squared plus 2 minus x squared minus 1/2. Now we're gonna integrate with respect to x, and that's give us, we simplify first, sorry, the 2x squared minus x squared give us x squared, 2 minus 1/2 equals plus 3/2. So now we integrate with respect to x. X squared becomes x cubed over 3, and for 3 half, we just had x, so that's become 3/2 x. That's going from 0 to 1. So since if we replace the x's by 0, those gonna be 0. So we just go and we replace x by 1. So x 1 cube is 1. So it's 1/3 plus 3/2 times 1, which is 3/2. So 1/3 plus 3/2 equals 11/6. So the required volume is 11/6.
Nice. Thank you, Liz. Gabriel. Then GE, last one.
Okay, so I decided to present on 5.212, and I put the question up here where it's basically asking us to combine our knowledge of Fubini's theorem and our past knowledge of the equality of mixed partial derivatives. So from the given, it says that f is continuous in R, so that opens up the portal to making theorem 1 of section 3.1 and of course theorem 3 and 3 prime of section 5.2 true, since they require that f is a continuous function. So yeah, first I wrote down the given, and obviously you can interchange the integral from c to y and a to x and their position in relation to Fubini's theorem. And I also wrote down there that we're also using the fundamental theorem of calculus, because that's also what they use in the section. So I did it in both ways. So the first thing that I did for the first way was to derive both sides of the given equation with respect to y. So as you could see here, I did it once and I used that fundamental theorem of calculus, and then I did it again, and then I was basically given f, the function of, or sorry, f of x and y. And then so I did it again with the opposite way, where the double integral starts with a to x and then c to y, and I did it to respect to x. And so I just did the same steps again, where I used the fundamental theorem of calculus, and I also got f, like lowercase f of x and y, and so that was one way that was proven. And then the other way that I did was I started the opposite way using Fubini's theorem. So as you could see, I took the partial derivative, the mixed partial derivatives, and I put them inside of integrals, and then I just did your usual way of integrating them. So I did that both for the mixed partial derivative of x and y and the mixed partial derivative of yx. And I both got the same answer, the whole fxy minus fxc minus fay plus fac. And so since they're both the same, I got the same outcome for both, then I can equate both of them. And then again, relating to Fubini's theorem, I can just simplify it all to dA, and then again, they're both equal to each other. So yeah, basically Fubini's theorem is just like the integral method of proving that mixed partials are equal to each other.
Nice. Thank you, Gabriel. Thank you. Jing E, the last one.
Okay, so I'm presenting section 5.1, question number 12. So this basically is just doing like I used this is the double integral from integration of like 1 to 3, and the integral of 1 to 2, the xy or x squared plus y squared to the 3/2 dx dy. So first I do the integration of x dx. So I treated y as a constant, so I can factor out the y and do the integration of x over y squared plus x squared to the 3/2 dx. Then I apply the u substitution, the u equal to y squared plus x squared. So the du will be 2x, and the x will be 1/2 of du. So I am placing back to the equation. I got integration of 1 to 3 times y times the integral of 1 to 2 from 1 over 2u to the 3 over 2 du dy. And then I do the power rule of the u, and I got the integral of 1 to 3 y times the half times the negative 2 over reg of u from 1 to 2 dy, and I plug in back to the numbers, that 2 minus 1, which is I got the integral of oh, and I also place back to the u into y squared plus x squared. So the final answer I got like the integral 1 to 3 negative y over y squared plus 4 to the 1/2 plus y over the y squared plus 1 to the 1/2 dy. And then I do the integral of y. Then I got let me see. Yes, I do the same things as a power rule, and I use the u substitution one more time, which is u equal to y squared plus 4 du to y equal to du over 2, and then the v equal to y squared plus 1, dv equal to 2y, the y equal to dv over 2. So I got the integral from 1 to 3, negative 1/2 times the u to the negative 1/2 du dy, plus the integral from 1 to 3, 1/2 times the v negative to the negative 1/2 dv dy. And then I do the integration of the power rule, and then I got a negative 1/2 times the 2 times the y squared plus 4 to the 1/2 from 1 to 3 plus 1/2 times 2 times the y squared plus 1 to the 1/2, also from the 1 to 3, and then I plug in the number to the y. Then I got the final answer equal to a negative radical 13 plus the radical 5 plus the radical 10 minus the radical 2.
Okay, thank you.
Thank you.
Anyone else like to present? Okay, I guess it's my turn. So today we're going to talk about integration over more general regions. So which is 5.3. And let's see if we have time to cover 5.4, 3, 6, change of variables. All right, let's go to section 3. So basically, we can see from these pictures. So these are called y simple. Y simple means in y direction, the lower limit and upper limit of the integration are functions of x. So the value of y depends on x. So that's a dependency here. So x direction we can set up from a to b are numbers. But a y direction we see lower limit is a phi 1 of x. The upper limit is a phi 2 of x. So we call this y simple region. X simple means x direction can be written as a function in terms of y. So x is written as a function in terms of y. We see y direction goes from c to d. So our numbers, but the x direction, the lower limit of x is per c1 of y. And the upper limit is also a function in terms of y per c2. Right, so those are similar, so 3 different situations. If we look at this unit disk, right, it could be a x simple region, it could be a y simple region. So we see this upper, if we see, if it's a y simple region, we look at the first picture. X direction goes from -1 to 1, but a y direction goes from a function, the upper semicircle, which is square root of 1 minus x squared. The lower limit is negative square root of 1 minus x squared. Or we can treat it as x simple region, right? The y direction are fixed. Lower limit is -1, upper limit is 1. But lower limit of x is negative square root of 1 minus y squared. Upper limit of x is the square root of 1 minus y squared. So there's a dependency here. So we won't be able to use Fubini's theorem anymore, because Fubini's theorem requires the lower limit of upper limit of double or triple integration, all the lower limits, all the upper limits to be numbers. Right? But here we have upper limit or lower limit to be functions. So there's a dependency. You see this is dy dx, dx dy. Oh, in this case that's okay because we have a rectangular region where integrate this integrand over this rectangle region. So then Fubini's theorem can be applied, which means it's free to change the order of integration. Sometimes maybe integrating in one variable is easier than the other variables. But with the dependency, it's different. It's different. It's the change of order of integration, it won't be free anymore. Right. The evaluation is still the same. Let's see this one. So example 1. So the integrand is this, x cubed y plus cosine x. Right? T region is given as this. X direction goes from 0 to pi over 2, so that's x simple. Y direction goes from 0 to x. So 0 is a number, but x means the line of y equals to x. So the picture is this. Right? So y, so what is x? So this is called a y simple. So this is the phi 1. Phi 1 of x equals 0. Phi 2 of x equals the x, identity function. So phi 1 of x equals 0. That's just x-axis. Phi 2 of x equals the x. That's just y equals the x line. So this region, x value from 0 to pi over 2, y region goes from 0, y value goes from 0 to y equals to x. So that's this triangle. So with this general region, x simple or y simple, we need to draw the right picture of the region. Okay. So see this one, the region we're integrating upon or over is this rectangle. No, not rectangle, triangle, is this triangle. So once we have this picture, we can set up our integration. So x direction goes from 0 to pi over 2. Y direction goes from 0 to x. Okay, what is the crucial difference from before? You see the variable with constant lower limit and upper limit are set up as outside layer. All right, lower limit 0, upper limit is pi over 2, so it's outer layer. The one with the lower limit or upper limit has a dependency, we set as the inner layer. So this is a crucial difference from before. Before our lower limits, upper limits, all numbers, we can apply Fubini's theorem. Now we cannot because there's a dependency. one variable depends on another variable. So the dependency one, the dependent one we put inside. The independent one we put outside. Because once we integrate no one, it becomes a function of x. Right? So we integrate with y direction, we get this. Then we evaluate from 0 to x. So we get a function of x. So the inner integration becomes a function of x. Then, because x direction, we have lower limit, upper limit to be numbers. So we can integrate, then in the end, we get a number. Well, this number just irrational number. You don't really have to approximate. If you put into a calculator, it will approximate for you, but for us, this is perfect. Okay. Leave as irrational number is perfect. Anyone has any questions? So that's the only difference from before. Let's see this example. Find the volume of this tetrahedron bounded by plane y equals 0. What is the plane y equals 0? Which is the xz plane. Z equals 0, which is the xy plane. X equals 0 means it's a yz plane. And this plane, y minus x plus z equals 1. All right. So the picture is this, tetrahedron. Tetrahedron. So we set up integrals. Right? So we need to, so first, what's our integrand? We need to figure out our integrand. We need to figure out the region. We'll integrate the integrand over. The region on xy plane, you could calculate the region on xy plane, on yz plane, on xz plane. That's no problem. But by convention, usually we go with xy plane. So xy plane, we see that's a triangle, right? That's a triangle. So we need to fix one direction. We could fix x direction or could fix y direction. Then we find out the dependency of y in terms of x or x in terms of y. So we have a choice. Let's see this one. So the textbook says, okay, I want to fix my x direction. Right, my x direction goes from -1, 0 to 0, 0. Then my y direction goes from 0 up to this line. This line, if you have 2 points, you can find the line representation, right? So in this case, that's y equals to x plus 1. Or the lower limit of y is 0. The upper limit of y is x plus 1. So this needs a little bit of work. Well, actually, this is given. Actually, this is given. If sometimes it's not given, we need to calculate ourselves. Okay. Most often, we need to calculate ourselves. So the region is a triangle. So we can set up. So x direction goes from -1 to 0. Y direction goes from 0 to 1 plus x. Then the integral is 1 minus y plus x. Where does that come from? So this is given as y minus x plus z equals 1. We want the integrand to be z, right? Remember z equals f of xy. So we rewrite z equals to 1 minus y plus x, right? Z is our integrand. F of xy is our integrand. Why? Because we choose the region to be on xy plane. And we fix x value goes from -1, 0 to 0, 0. And we figure out the y direction goes from 0 to x plus 1. So our integration is over xy plane. So x direction goes from -1 to 0, y direction goes from 0 to 1 plus x. So that's why the integral has to be z. So z equals to f of xy, or 1 minus y plus x. Then we integrate. We integrate with the y direction, we get a function of x. Then we integrate with x direction, we evaluate from -1 to 0, we get a 1 over 6. Anyone has any questions? Okay, let's keep moving. Similarly for x simple region, or x simple region, for y simple region, which means y has, let me see if that's an example of y simple region. It's all dy dx, dx dy. Yeah, you see this one is a y simple region, right? So y direction goes from -3 to 2, and x direction has a dependency of y. So perceive 1 of y equals 0, perceive 2 of y equals y squared. Okay, so this is the y simple region. But when you integrate, you just don't care, right? You integrate the inner one first, you get a function of y, then you integrate with y direction. Okay, let's see 5.4, change the order of integration. Because sometimes the integrand is really difficult to be integrated in one direction with one variable. So then we want to change the order of integration. Let's see this one. The integrand is f of xy, and we want to integrate over the region D. The region D might be x direction, a constant. Y direction has this independency. Lower limit is a function of x, upper limit is a function of x. And then maybe the integrand is very difficult to integrate in y direction first. We want to change to be integrating x direction first. So we want to integrate in x direction first. In that case, we need to recalculate. Most of the time, we want to draw a picture of this region D. So x direction goes from A to B, that's easy. Then the lower limit is a function of x, right? We draw the picture, we draw the graph. The upper limit is a function of x, we draw that graph. Then we see the region. Then maybe the region can be reinterpreted or re-represented. Y direction goes from C to D. Then we figure out the x direction, right? We figure out the dependency of x direction in terms of y. So what is the relationship between phi1 and psi1? Like inverse functions, right? Because this one is y equals to psi1x. So y is a function in terms of x, and this is x is a function in terms of y. So phi1 and psi1 are inverse functions. Phi2 and psi2 are inverse functions. Let's see this. Let's see example 1. So the integrand is a squared minus y squared. So a are some numbers, all right? A squared minus y squared, then square root. So we want to integrate it in the y direction first. That's very difficult, right? Because we have inside we have y squared, but the outer we don't have y. If we have y multiplied by a squared minus y squared, square root, that's easy. But here we don't have y, we have y squared under the square root. So it's very difficult to integrate in y direction. So what do we want to do? Because this has no x in it. In x direction, this is just a constant, just a number. So we want to change the order of integration. So what do? We draw the picture of this region. Well, x direction goes from 0 to a. Y direction goes from 0 to square root of a squared minus y squared. That's a half semicircle in x direction. Okay? We just draw the picture. Oh, from 0 to a, 0 to that's quarter circle, right? 0 to x direction goes from 0 to a, y direction goes from 0 to square root of a squared minus y squared. Just this quarter circle. Well, once we have this quarter circle picture, we reread, right? Let's see, we fix y direction. So y also goes from 0 to a, right? Y also goes from 0 to a. What about x direction? X direction goes from 0 to this quarter circle. What is the representation of this quarter circle of x in terms of y? It's just x equals to square root of a squared minus y squared, okay? So y equals to square root of a squared minus x squared, because the circle with radius a is x squared plus y squared equals to a squared, right? So x and y, so it's a symmetric equation, x, y equally weighted. So we want to change the order of integration from dy dx to dx dy. So we want to change, so once we change the order of integration, we need to change the lower limits, upper limits in both directions. In this case, because this is a symmetric equation, so x and y are equally weighted, we see y direction still goes from 0 to a, and the x direction goes from 0 to now square root of a squared minus y squared, right? So that's the function of x in terms of y. Now, because we're integrating x direction, and this is just a constant in x direction. So once we integrate, we just get this multiplied by x, it becomes a scalar. Then we evaluate at 0, evaluate at a squared minus y squared square root. What do we get? We get a squared minus y squared, right? Then we evaluate in y direction. Well, a square in y direction becomes a square y. Negative y square in y direction becomes a negative y cubed divided by 3. Then we evaluate from 0 to a, get to a cubed divided by 3. So this is a change of order of integration. Anyone has any question? So the step is, if look at the integrand, we see, oh, that's difficult to integrate. We need to change the order of integration. Then we try to draw a picture of the region. Very important to draw the right picture of the region. Then we figure out the representation of the region in another way. Let's see more examples. Let's see this one. The integrand is x minus 1, square root of 1 plus e to the 2y. We see e to the 2y is going to cause problem, but because we don't have e to the 2y outside the square root. So in y direction is difficult, but this inner one is dy. Right away we think, okay, I need to change the order of integration, because if I integrate the x direction, that's easy. It's just linear, right? X minus 1. And this becomes a scalar in x direction. So what do we need to do? We need to draw this region. X direction goes from 1 to 2. Y direction goes from 0 to log x, goes from 0 to log x. So pre-calculus knowledge, we need to be able to draw this region. Then once we have the region, we want to represent it in another way. We look at y direction. Y direction goes from 0 to log 2, right? The lowest value is 0. The highest value of y is log 2. Then what about x value? X value goes from this function, this graph. Well, what is this graph in x direction? So y equals to log x can be rewritten as x equals to e to the y. By the way, a lot of textbooks read log in terms ln. Okay, this log we can treat as a natural log, ln. So this we can be written as x equals to e to the y. Right. So the lower limit of x is e to the y. What's the upper limit? The upper limit of x is 2. So that's the crucial part of when we change order of integration. Okay, we draw the picture of the region, then we represent the region another way. All right, so y direction, we have constant lower limit and upper limit now goes from 0 to log 2. And x direction goes from e to the y to 2. Now it's easy to integrate x minus 1 because this is just scalar. We can put outside the integration. Once we integrate the x direction, we get a function of y. So miraculously, we see e to the 2y, e to the y now. Now we can split into 2, e to the 2y, e to the y. Okay. If you want to use u substitution, so we need u, v, okay. substitute, evaluate. In the end, we get a such tedious number, the irrational number. But this is exact. Okay, we don't need to approximate. Anyone has any question? So change of order integration when the limits involve dependency of one variable in terms of another. We need to draw the region. If the integrand is difficult to integrate in one way, so we draw the region, we represent the region in another way. Mean value equality. It's not important. All right, so basically that's for today. All right, change of order in integration. Then next class, we're going to talk about the triple integral. We're going to chapter 6. Dayeli, question?
Yeah, I was just gonna ask. Yeah, the same question that Gisela is asking. Like, the midterm is next week. When are we gonna get the midterms grade back as well?
Midterm, I can only see as soon as possible. Okay. Yeah, it takes time to grade the midterm. And the final, yes, cumulative, but more towards, it would be like 30 to 40% of the previous one, and 60 to 70% of the later one. Yeah, final will be accumulative. Okay, so we have 1, 2, 3. Right, we have 3 classes. Up to what section? Let's see. Let me go back. Okay, it's time to talk about the final. Yeah, I haven't found, I'm trying to find someone to proctor the final exam for me on campus. And yeah, so I will let you know. All right, so next class we'll start triple integrals. Then once we finish triple integrals, we're going to jump into 6.1. I'm going to, brush very quickly. Then focus on 6.2, the change of variables, because we want to use, sometimes the integral is very difficult to integrate over x, y, z coordinates. We want to change it to be polar coordinates, even cylindrical and spherical. And then once we change the order of coordinates, the miracle happens. So chapter 6 basically is just 6.2. Chapter 7 maybe, let me see, or line integrals. You know what? I'm not even going there, all right? So we'll finish by chapter 6, change of variables. So we will have one class to do review. For chapter 6 homework, can we just do 6.6.2? You're exactly right. You're exactly right. Okay, any other questions? Okay, we're not going to chapter 7. We're going to finish by chapter 6, and let me see if we should talk about improper integrals. If we have time, maybe we'll touch on improper integrals. It's very similar, it's very similar to single variable calculus. The difference is just to deal with a variable one at a time. If there's independency, if the integrand is difficult to integrate in one direction, we change the order of integration. And if the integrand is difficult to integrate over x, y, z plane, we change to be polar coordinates. Gabriel, can we have the final the same way we did the midterm? You mean online? School requires every final to be online, all right? Every final to be on campus. So all right. So next class we're going to talk about triple integral. Okay, triple integral, 3 dimensions with the integrand 4 dimensions. So you can imagine it's a volume for 4-dimensional object, which we cannot imagine, but which is okay. All right, if you don't have questions, you're free bird, go ahead, start your homework. And if you still have questions, I'm here. Yes, Liz?
Yeah, Professor, you said you will do number 12 from the midterm today.
Oh, okay. Yes, Liz has a question about the midterm 12, question 12. Let's go over that. Okay, number 12, let me make this a little bigger. Find the absolute maximum and minimum value of this. Okay, Liz, let me ask you. This is over unit. Yes.
We can't see it.
Oh, sorry.
It's okay.
I have to raise sharing. Let me share again. Can you see it now? Oh no, you still don't see it, right?
Still
yes,
loading.
it popped up.
Yeah, we're good.
Oh, okay.
Yes, we can see.
So let me ask you a question. Okay, we want to find absolute maximum minimum. You know the method, but the only difficult thing is this over
yes, it's the
unit.
discontinuity.
Yeah, so you have to separate it into 2 parts, right? The first part is x squared plus y squared less than 1, which is open set. How do you find the absolute maximum minimum over an open set? First derivative test and a second derivative test, right? So that's the
Yes.
first part, over the open set. The second part is the boundary of this, which is x squared plus y squared equals to 1, which is a closed set. How do you find maximum and minimum over a closed set? Lagrange method. So this require both. Require you use first derivative test to find the critical points over the open set. Then you use Lagrange method, Lagrange multiplier method to find the critical points on x squared plus y squared equals 1. Then you evaluate, once you find out the critical points, you evaluate the function value. Whoever is the biggest, that gives you maximum. Whoever is the smallest gives you a minimum. The ones in the middle, you don't care, just ignore. Make sense?
Yes.
Okay, try that.
Okay, thank you.
You're welcome. Anyone has any other questions?
Yes, Professor, I have a question.
Yeah.
So, will there be any questions from sections that were optional or no?
No.
Okay.
No.
Thanks.
If the section is optional,
Mm-hmm.
it won't appear in any of the exams.
Okay. Thank you.
You're welcome.
Alrighty. Have a good morning.
Oh, thank you.
Of course.
Thank you.
Bye-bye, Professor.
Have a good evening. Do your
Okay.
homework.
Yes, ma'am.
Okay. Thank you. Okay. Any other questions? Thank you, Liz. Thank you. Thank you. Thank you. Thank you, Junyi. Thank you.